Back to part 2. Another problem. Another airplane. Look at this. Alright, so this time we have an airplane that's flying 240 miles at a bearing of 25 degrees. So again, it's bearing. It's going to be our navigation. So I draw my axis system. Here's north. Its bearing is 25 degrees. We measure this way, 25 degrees. And it's traveling a distance of 240 miles. Then it turns and flies 160 miles along a bearing of 130 degrees. So be careful. See, the bearing says it's measuring from the north and it's going to go 130 degrees. It's not saying it's going this direction and turns 130 degrees. So I have to draw like another quick little axis system. There's north. Go 130 degrees. Be right over here. And I draw it out. And it only travels 160 miles. And that's where the plane ends. So the question remains, we know this is 130 degrees. The question now is, how far does the plane travel and what's the bearing? So there's our resultant vector. So again, I'm going to blow this up, make it a little bit bigger so we can kind of see it. There's a lot of writing on here. We know this is 240, this is 160. Now they didn't directly give us any angles, but we can kind of guesstimate, right? If I draw this out, I know this is 90, right? So this angle right here had to be 40. Because remember, 90 and 140 had to equal 130, which means this little part right in here is 50 degrees. So the next question is, well, what is this angle going to be? We actually know that. We have to go back to old school. Remember, this angle right here is 25 degrees. By drawing these two little bearings right here, remember, these two lines are parallel. So if this is 25 degrees, this is also 25 degrees. So if I draw it out again, just to make sure it looks pretty, because I like pretty things, this is now set 25 and 50, 75. This is 240, and there's 160. This is my resultant vector. Right there. There's R. Can we now find R? Yeah, absolutely. It's going to be our law of cosines. So to get R, right, we know R squared equals 240 squared plus 160 squared minus 2 times 240, 160 times the cosine of 75 degrees. Mine's all kind of small there. Now, I already did this ahead of time, so I'm just going to go ahead and give you guys the answer. R here is 251.64 miles. So the plane traveled 200, did not travel this far, but the plane is 251.64 miles from where it started. Okay. Now, you all hear about this plane that got lost in the Indian Ocean. A lot of what they're doing is that they're chasing the bearings of the plane. How far did it travel at this bearing? How far did it travel at this bearing? They're just using our vectors to try to find out where that plane might have crashed. All right. The next thing we have to do is get the bearing. All right. To get the bearing, we have to find theta. And of course, we again can use law of sines. We know, always the old-fashioned way, sine of theta is over 160 equals the sine of 75 over 251.64. Now, unfortunately, I didn't do this one ahead of time, so I'll do this one right now. So we're going to take the sine of 75, multiply by 160, so 160 times the sine of 75, and then I'm just going to divide that by 251. 251 point, what was it again? 64. And that gives me 0.61. Be careful, that's the sine of theta, right? The sine of theta equals 0.6142. To get theta, second sine, second answer, we get 37.89 degrees. So there's my theta here. It was, again, 37.89 degrees. But remember, the total bearing is this. This is my total bearing right in here, theta. So to get the bearing, the actual bearing, we're going to take, well, we're taking this 25 degrees that we're already at, 25 degrees, plus we just found this little theta right here of this 37.89 degrees. And we add those together, and that becomes 62.89 degrees. That's our bearing. So let's go ahead and write this out. Let's write out our answer. Remember, it's a little bit trickier to do. We traveled the distance was 251.64 miles at the bearing, spread it out 62.89 degrees. Starting from the north, we traveled in an easterly direction. And there's our answer. So practice this one again if you need to, okay? Bearings are a little bit different. They're a little tricky to do, okay? We're going to take a look at more examples tomorrow, of course, as a class. All right, let's take a look now at example number 3 here. These are kind of fun. These are a little bit easier, okay? All right, now for example number 3, let's call these course problems. Notice there's no the word bearing in here. So this is just like normal, okay? This is normal. We're not going to measure from 90 degrees. So let's take a look. We have an airplane traveling in the direction of 200 degrees. Since it's not bearing, we're going to draw this normally. So in other words, the x positive is our 0 degrees. So if my plane is traveling at 200 degrees, we know the plane is heading in this direction, with theta equaling 200 degrees. And it's traveling at 250 miles per hour. Now, what's happening is there's a 35-mile-an-hour wind at 285 degrees. So what's that going to do to the plane? Well, the wind is pushing in this direction, it's 285, so it's going to move the plane slightly south, okay? And pilots actually have to compensate for this. So that's the plane. So let's take a look at the wind. Well, the wind is going at 285 degrees. That's going to put us in quadrant 4 here. Here's the wind. And it's moving at 35 miles per hour. What we want to know is, we'll find the plane's ground speed and course. Well, the ground speed is easy. Because the wind is going in such a direction, it's actually going to push the plane. It can make it go faster or slower, depending on the direction of it. Because imagine if you have wind pushing, if your plane is going in this direction, the wind's coming from behind it a little bit, it's going to make it go faster. If the plane is going in this direction, the wind is actually going to slow down the plane a little bit. And we can actually find it using trigonometry. And that's what we're going to do today. So how do we do it? This is just our head-to-tail method. Head to tail. Now, for those of you who don't know, head to tail is basically just adding vectors. So I'm going to take the tail of the wind and put to the head of the plane, like so. And I'm going to look for the resultant vector. So we're just going to add the vectors. So here's what we're going to do. We're going to take the plane's vector, look at that for fancy, plus the wind's vector, and that's going to equal our resultant vector. So how do we get the vector of the plane? Well, we know that this is just our, to get x, this is just our magnitude, cosine theta. Y is the magnitude, sine of theta. And they give us all of that. We have the magnitude, the speed, that's the magnitude, and we have the direction, there's our theta. So to get the plane, I'm going to get, so for x, for the plane, it's going to be, to get x, the change in x, right? Change in x, change in x, change in x, just change in y, sorry. It's going to be 250 cosine of 200. To get the change of y, 250 sine of 200. So our delta x for the plane, if I just type all of this in, clear, 250 cosine of 200 is negative 234.9. I'll go to the 10th place. Delta y, let's go 923. Delta y, 250 sine of 200. And that's negative 85.505. So I can write the plane's vector as negative 234.923, comma, negative 85.505. And I do the same thing for the wind. For the wind, delta x, it's going to be, the wind, its magnitude is 35. Its angle, they tell me, 285. So 35 cosine 285. Delta y is 35 sine of 285. And I'm just going to type those in my calculator. Okay? 35 cosine 285. And I get 9.059. And I get 35 sine of 285. Negative 33.807. Now, x is positive, y is negative. We should expect that because the wind was in the fourth quadrant. So I'm going to add to that the wind's vector, which is this, 9.059 negative 33.807. And if I add them up, I get my resultant. This is my resultant vector. It's going to equal 234, negative 234.923 plus 9.059, which gives me negative 225.864, and I'm going to take this negative 85.505 minus 33.807. And I get negative 119.312. Now, that's my resultant vector. But remember, we're not looking for just the resultant vector. We are looking for two things. The ground speed, which is just the magnitude of our vector, and the angle, the course, that's the angle. Okay? So to get speed, that's just magnitude. I can just take this 225 square root, sorry, 225.864 squared plus, I don't worry about the negatives because I'm squaring it, 119.312 squared. And I get 255.441 miles per hour. So the plane, even though the plane is traveling at 250, according to an observer on the ground, it's actually moving at 255 miles per hour because the wind is pushing it. Now, to get theta, we're going to do the inverse tangent of our negative 119.312, negative 225.864, and see what that gives us. Now, I worked this out ahead of time, but we're going to get the answer. Second tangent, negative 119.312 divided by negative 225.864, and we get 27.85 degrees. But you got to be careful. Look at this picture. 28.7 degrees. That's actually moving north. We're moving in which direction? Southerly. Okay? We are actually in our answer should be in quadrant 3. So this should be a quadrant 3 angle. So how do we get the quadrant 3 angle? Theta equals 180 plus this 27.85. So the theta should actually be 207.85 degrees. And there's our angle. Sorry, I ran out of room. All right, so try problem 3. We'll take a look at this tomorrow, and we're going to do a whole bunch of other examples tomorrow in class 2. I promise it will be fun. Okay? We'll see you then.